Hi, I am Yoshi Yurimoto of Hokkaido University. I am glad to see you all through this online plenary. I hope you all stay safe and healthy from the coronavirus pandemic. My talk of today is Age of Asteroid Sample Return. We are living in the age. In the left is Hayabusa and an asteroid Itokawa. The right is Hayabusa 2 and asteroid Ryugu. In the center is OSIRIS-REX and an asteroid venue. I would like to talk about scientific results of mainly these missions. Firstly, we will see the history of sample return missions. As you know, our first sample return of extraterrestrial materials was from the moon by Apollo program. The last one was by Apollo 17 in 1972. After that, we have a log blank more than 30 years for sample return mission. In the beginning of 21st century, we made a cometary material sampling by Stardust program and solar wind sampling by Genesis program. Then in 2010, we got an asteroid sample in the laboratory by Hayabusa program. Now, two asteroid sample return missions, Hayabusa 2 and OSIRIS-REX, are ongoing. Why do we go to asteroids? Because we learned a lot of evidence for origin of solar system from chondrite. As you know, chondrite consists of materials formed in the early solar system. We can analyze how formed the materials are in the laboratory. For example, this picture is a chondrite named iron meteorite. We can analyze chondrules, matrix particles precisely, for example, using by EPMA and by SIMS. However, before Hayabusa program had been completed, we did not know where the parent asteroids of chondrite were from. In other words, where the early solar system material preserved in the solar system space. By the way, we knew some orbit of meteorite before Earth entries, as shown in this figure. A failure of these orbits were positioned in asteroid belt. These meteorites belongs in a group of near-Earth asteroids. Near-Earth asteroids are good target to collect samples because they are easier to go economically using a small rocket. Why did we select an asteroid Itokawa for the first target to go? Because Itokawa is one of near-Earth asteroids called Apollo asteroids. Orbit of Apollo asteroids are positioned in the green area in this figure. The M is mass orbit and E is the Earth orbit. The aphelion of Apollo asteroid is around the mass orbit and the perihelion is inside the Earth. This is the orbit of asteroid Itokawa. It is shown by I. The asteroid Itokawa was the only asteroid that Japanese rocket Mu-5 could arrive at when it was launched. This was lucky and a good target because this is the first challenge to collect asteroid samples. Furthermore, Itokawa might correspond to the most abundant meteorite class found in the Earth. Hayabusa was launched in 2003 by the Mu-5 rocket at Uchinoura Space Center, Japan. 2 years later, in 2005, Hayabusa was arrived at asteroid Itokawa. This computer graphics is based on the flight recorder of Hayabusa. The sampling on Itokawa was 2 times. We call the sampling method touchdown. Just before first touchdown, Hayabusa detected alert signals. Then Hayabusa was plunged into a panic and spent 30 minutes on the Itokawa surface. After recovery, we revised the algorithm of touchdown sequence and tried to the second touchdown. The second touchdown seemed to be succeeded. But we missed an important sequence of sampling. The nominal sequence is that our bullet was shot at touchdown, as shown in this computer graphic. In order to smash the surface materials and collect the splashes, this bullet shooting had not been operated because the programming update had not complete. Therefore, we were not able to estimate how many samples were there in the sample catcher. This is the sample catcher of Hayabusa. And these are parts of the inside. Here is a room for samples. The left one is a real one and is now in the curation chamber in the next slide. As inferred, there were no visible samples in the room. So we use a micromanipulator to pick samples up. This is the curation chamber of Hayabusa samples. A manipulator is inside of it. These 2 persons are just use the micromanipulator to picking sample up. The picking work is now still continued every day, every morning in the working day. We try to pick samples larger than 10 micrometer in length, and the total number picked are now more than 100 particles. The size is 35 micrometer on average, and the max one was 270 micrometer. About 350 particles have been distributed to scientists in the world. This is a backscattered electron image of a typical grain from Itokawa. The left image is as collected, and the right image is the same one after surface polishing. We measured oxygen isotopic composition of composed minerals. This is because Professor Bob Clayton discovered meteorite parent bodies and planets are characterized by their specific oxygen isotopic compositions. This is the oxygen 3 isotope diagram plotting Clayton's old data measured in his laboratory. Solar system objects are not only plotted on the terrestrial isotope fractionation line, but also on the slope-1 mixing line. The slope-1 relationship is called the famous oxygen isotope anomaly in the solar system. Recent studies found the oxygen isotopic anomaly was much wider toward 60-rich direction, as well as toward 60-poor direction. McKeegan showed that 60-rich end member seems to be the composition of the Sun from results of Genesis mission. Sakamoto shows that the oxygen 16 poor end member seems to be a pristine water vapor in the early solar nebula from a primitive chondrite Aspa 094. This oxygen isotope distribution in the solar system is consistent with our model. And the model proposed that oxygen isotopic composition of the planet are 60 or poor planetary oxygen isotopic compositions. This figure shows oxygen isotope variation among chondrite parent bodies. All chondrite parent bodies have planetary oxygen isotopic compositions, and the isotope compositions have small variations each other. Oxygen isotopic compositions of individual minerals in Itokawa particles are shown in these red plots. The data plotted along an Itokawa isotopic fractionation line and crossed at the LL chondrite position. Oxygen isotope symmetry determined by the isotope fractionation shows that the minerals formed at 700 degrees Celsius. Mineralogical studies by Nakamura consist with these results, but the forming temperature is slightly higher at 800 degrees Celsius. From mineralogical and oxygen isotope studies, we clarify Itokawa is a LL5 chondrite. Therefore, ordinary chondrites, which are about 80% of meteorites fallen to the Earth, come from asteroid belt. Forming conditions of minerals in Itokawa were at 800 degrees Celsius, and the heating period was a million years. Therefore, size of the parent asteroid minerals formed was larger than 20 kilometers in radius, but the size of Itokawa is only 500 meters in major axis. So Itokawa is not the parent asteroid of the minerals, but the fragment of the parent asteroid. This is the whole history of asteroid Itokawa from material analysis. At 4.5 GA, parent asteroid of Itokawa was formed in asteroid belt. At 1.4 GA, asteroid collision occurred, then asteroid Itokawa was formed from the fragment. Itokawa migrate to Apollo asteroid orbit by 100 MA, which is inferred by cosmic irradiation age. Solar wind irradiation age inferred that small surface sliding occurred in the time scale of 1,000 years. This event recorded on the crystal surfaces as microstructure as shown in the upper SEM pictures. Decoding the asteroidal surface evolution is unique research topic only from return sample because meteorites lost their surface layers completely by aberration when they entered the atmosphere. So I would like to focus on mineral surface evolution to be accurate, mineral surface aging by solar wind irradiation. Solar wind irradiation is one of the important processes of space weathering. This blister structure was generated on crystal surface by high solar wind fluence. This is a magnified SEM image of mineral surface. Blister structure is developed. This TM image is a cross-section of the crystal. These vesicles correspond to the blisters of upper image. The vesicles are footprint of degassing of helium implanted by solar wind. The three figures in the right are three-dimensional distribution map of helium concentration in an Itokawa particle surface. Implanted solar wind helium is concentrated in the layer at 30 nanometer beneath the surface. These novel analytical techniques reveal the material evidence of space weathering developed on asteroids. This is a mass distribution of main belt asteroids. X-axis is the same major axis from the Sun. At the inner main belt, S-type asteroids are dominant. Itokawa parent asteroid would be located here. Itokawa samples demonstrate ordinary chondrites come from here. Instead, the middle of main belt, C-type asteroids are dominant. So next sample return target after Itokawa should be C-type asteroid. C-type asteroid may bring a key of origin of life. So Hayabusa 2 and OSIRIS-REX had launched toward C-type asteroids, Ryugu and Bennu. These are asteroids, Ryugu and Bennu, taken by Hayabusa 2 and OSIRIS-REX. Ryugu is a C-type asteroid and Bennu is B-type. B-type is a subtype of C-type. We expect that materials of both asteroids are kind of carbonaceous chondrite. The surface colors are black. The albedos are very dark, comparable to carbonaceous chondrite for Bennu, and darker than carbonaceous chondrite for Ryugu. Both asteroids have an infrared absorption band of 2.7 micrometer suggesting existing of ferrosilicate. The abundance of the ferrosilicate, in other words, water content of asteroid, may be smaller in Ryugu than in Bennu. These surveys by OSIRIS-REX and Hayabusa-2 confirmed the linkage among carbonaceous chondrites and these asteroids. OSIRIS-REX is now in the sampling rehearsal mission phase. The sampling action is called touch and go, as shown in this figure. This is a movie of sampling collection rehearsal in April this year. The center arm is a sampling apparatus called taxam arm. The first touch and go sample collection by OSIRIS-REX is scheduled on October 20 in this year. The site is in this site. We are looking forward to that day. Hayabusa 2 has succeeded touchdown on Ryugu 2 times in the last year. This is a movie of the first touchdown sample collection. Hayabusa 2 was descending, 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 and touchdown now. We are surprised because surface materials of Ryugu were very fragile. The materials were easily broken up and the fragments were thrown up like confetti. This fragile property was confirmed by thermal inertial measurement from Hayabusa 2. The measurement inferred microporosity of surface materials on Ryugu is 30 to 50%. Such high porous materials have not been reported from any chondrite so far. Hayabusa 2 may return new chondrite to the Earth that we have not known. Hayabusa 2 is now in the return flight phase. The re-entry date will be in early December in this year. This is a movie of Hayabusa re-entry. Hayabusa 2 will be similar shape, but only re-entry capsules will be returned, and the rest of the Hayabusa 2 stayed in space. The landing site will be in Australia. The re-entry capsule will be quickly brought to JAXA, Japan. This is a curation facility to curate Ryugu samples. The facility in the movie is in the middle of construction. Now, the facility is completely installed as shown in this picture. The re-entry capsule will be opened in the chamber and prepared for scientists in the world. The initial analysis of Ryugu samples will return in June in the next year. Hopefully, some of the first report will be presented in the next Goldschmidt meeting in Lyon. Thank you very much for coming to my online plenary. Thank you very much.